Thank you, Luis, and thank you for the opportunity of presenting this work. Initially, I started with a very brief introduction to TV blazar jets. I know that most of you will know better than me what I'm talking about, but for the laser part of the talk, it's better just to give a little bit of background. So blazar jets are essentially active galactic nuclei with a jet which is directed towards the Earth. And they are powered by material accreting on a supermassive black hole. And blazars are powerful sources of emission of electromagnetic radiation. And we are concerned mostly with those gamma ray bursts, those blazars that emit in the TeV region. So we have a blazar here that emit TeV gamma rays. And what happens is that those TeV gamma rays do cascade by interacting with the infrared extragalactic light into pairs. So from the TeV gamma rays, you have a pair of electrons and positrons. So this jet then can do inverse quantum scattering with the CMB, producing on the order of 10 GeVs photons. So this seems what we should see. But the problem is that when we look at the spectra, which is measured from blazars, for those TeV blazars, we see the TeV emission, here, for example, data from S, but we don't see any GeV photons, at least not within the sensitivity of the instrumentation. So this is rather puzzling, and one of the possibility, one explanation, is that in the jet of electron and positron pairs, there are intervening magnetic fields that deflect the pairs outside the direction of the line of sight, and so the GeV gamma rays are emitted not in the cone of the observations. And people have been discussing this process, and this has been somehow some sort of controversy in some of the astrophysical community, because some argue that we know from simulations that electron-positron beams, when they interact with an ambient plasma, they become unstable. So there are beam plasma instabilities that develop and produce these self-generated magnetic fields. But then if you look at the papers that have been published, some people claim that those instabilities are growing very fast. Some other people claim the opposite. So then the explanation, another possible explanation is that these magnetic fields exist very early in the universe, for example, at the QCD crossover or at the electromagnetic phase transitions. And those are the fields that provide this external magnetic field. The problem is that in order to have the fields that are required to explain the absence of the GeV emission, those fields, as I said before, must be produced very early in the universe. And now the problem is that there is not a clear mechanism for production of magnetic fields very, very early in time. So as I said before, simulations, and there are many simulations, where you put a beam of electrons and positrons into a plasma, and what you see are structures like this one, so where the beam becomes unstable, and you have the formation of essentially magnetic fields leads to a separation of currents in an initially homogeneous neutral beam. And those instabilities then further amplify the magnetic field. So these are, there are many types of instabilities. Usually the fastest one are the Weibel or current filamentation instabilities, but then many other instabilities do play a role. All of this is done for very ideal conditions where the beams are collimated and there are only electrons and positrons with a background. But in reality, if we want to study the process, we need to include the fact that the beams have some divergence. So there is a transverse temperature which is not zero. There are some ambient perturbation in the intergalactic medium. And there are not just electrons and positrons and protons, but there might be many other components, hadronic components that can be becoming important. So all of this needs to be somehow addressed at some level. in particular if you want to do experiments. So now the question is, can we test beam plasma instabilities, pair beam plasma instabilities in a laboratory? So in order to do that, the first thing we need to do is to create a plasma of electrons and positrons. And some of the talks today showed about mechanism for production of electrons and positrons. Also, in this last session at the end, you're going to see other mechanisms for production of electrons and positrons. Most of the work initially has been done on laser facilities, where essentially you fire a laser into a IZ material, and this produces pairs of electrons and positrons plus gammas. The efficiency can be quite large, but these beams tend to be not entirely quasi-neutral, and they are also not really collimated. There are other techniques where you fire a laser into a plasma to produce a wake field. This wake field produces electrons beams of relatively high energy, which then interact on IZ material and produce a beam of electrons and positrons. This technique has been developed in the UK at the Rutherford Laboratory, but also at Livermore and other places. You get beams that are quasi-neutral and collimated, but the pair yield is not very large. Even people now think about improving these techniques. Or you can use accelerators, where you combine electrons and positrons. There should be a plus here somewhere, but sorry, electrons. Then you convert electrons into positrons, and you through chicanes. But all of this is not really available right now. So far, the main effort in creating electron-positron beams has been focused on high power lasers, right? So again, this is what you do with high power lasers. With one of the first experiments done, in this case at Omega, but also Lawrence Livermore, they did this type of experiments. So you fire a laser into a target, IZ target. You have these pairs. The pair angular distribution has been measured in the order of 10 to 20 degrees. So they are not really highly collimated. The spectrum of the pairs is this one here. So they are, you are about 10 to the 10 to 10 to the 11 pairs per MeV, and they extend up to 50 to 30 MeV, right? So these are the electrons and these are the positrons. And again, there is a bit of a difference between the two. And so the question is also what requirement that we need for a pair beam to behave as a plasma is essentially to be such that the skin depth or the bile length in the beam has to be smaller than the size of the beam itself. So this puts a requirement on the number of positrons that you have. And the other requirement that you need is that the beam has to be longer than the inverse of the plasma frequency in order for any type of instabilities to have sufficient time to develop. So we have a requirement essentially on the, so this puts a requirement on the number of electrons and positrons. The second condition here puts a requirement on the density of electrons and positrons. Now, if you put that on the table here, so this is the number, this is density, and the red dots here corresponds to experiments that have been done at laser facilities. The line here is where you want to be. You want to be above this line in order for these two conditions to be satisfied. So these are, you see that these two experiments are below the blue line. So the beam is not really behaving as a plasma, but the beam is just behaving as a collection of individual particles still. So there are no collective processes at play. So the red dots here, the red circle corresponds to proposals for future experiments at different laser facilities. Some of these laser facilities are not available now and won't be available for quite a long time. And the problem is that if you want to do an experiment now to test some of these processes, you cannot do it with the current laser facilities. So this brought us to think about why don't we do these experiments on a different system? So instead of using a laser, why don't we look at techniques using particle accelerators. And most of the work I'm going to present was developed by my student, Charles Arrowsmith, but also going to give a talk later in this session. Okay, so this is the work we do on CERN. So at CERN, we use one of the particle accelerator. We use the superproton synchrotron, here the ring. Most of you are familiar with LHC. So the role of the superproton synchrotron is to essentially act as the main injector for the Large Hadron Collider. However, SPS can also be used for individual experiments. So there are many end stations around the SPS ring. So we are going to use one of those end stations. The type of beam energy that SPS provides are protons of energy of 440 GeV. We can use up to 310 to the 11 protons per bunch. A bunch duration is 375 picoseconds. And in principle, one could use up to almost 300 bunches. And even with a single bunch, the amount of energy that a single proton bunch can provide is in the order of 20 kilojoules per bunch. So this is, in terms of people that do laser experiments, this is an incredible amount already in a single bunch. If we use all the bunches here, we have an energy which exceeds the largest laser available in the world, which is the National Emission Facility laser at Lawrence and Livermore. And sorry, it didn't come out here, but the peak power is in the order of 10 to the 17, 10 to the 18 watts per square centimeter. Okay, so which is quite impressive for this type of facilities. So this is the experiment that we designed, that Charlie designed. So it's, we have the proton beam coming from the SPS. The proton beam goes through a target, which is mostly composed of carbon. So as the proton interacts with the carbon, an hadron cascade is initiated. Among the various processes, we have a formation of pi zero. Pi zero has a very short lifetime in the rest frame of the laboratory rest frame, around 10 to the minus 20 something seconds. So it decays immediately in 2 photons. Those 2 photons then enhance Bethe-Heitler processes in the last part of the target, which is 10 millimeter of tantalum. So this reduces scattering of electron-positron pairs and allows for a beam to be as collimated as we can. Then we measure the number of pairs using screens, right, fluorescent screens, and we also have an electromagnet to measure the pair composition. So in order to prepare for experiment, we use a Monte Carlo code called FLUCA. Before people talk about Giant4, FLUCA is the competitor, even if the 2 codes are likely going to be merged in the next couple of years, because both the Giant4 and FLUCA come from CERN. And they realized maybe it's not a good idea to have 2 codes competing each other. And so these are highly tested code in all the particle physics community. They're used also for medical physics as well. And the type of processes that we are using in this type of experiments are pretty standard. So we expect FLUCA to be quite accurate in its prediction. So these were the predictions from our experiments. We see that we have a pair, so these are the electron and positrons distributions. We have a power law distribution with energies up to a few hundred MeV, right? So this, and you see that the number of electron and positrons in the prediction is very similar. We have a residual photon beam that is there, as well as some protons, which not all the protons are stopped by the target, and there's a large number of protons that remains unaffected by passing through the converter target. And also we have a minor number of other particles. In this case, what we plotted here are the pions, pi plus and pi minus, but there are also muons and neutrons and many other particles present. This is the larger number of particles. The other point to make is below 10 MeV, here the distribution is not equal anymore, but those particles, those low energy electrons and positrons, unlikely can propagate far enough for the type of experiments we want to do. So as I mentioned before, we want to measure the pair number. So the beam goes through a foil, which is a fluorescent foil, so emits visible radiation when charged particles or any particles crosses it. By accounting for the energy deposition for different species, we can evaluate, so in this case, when there is no target, so there are no electron and positrons, we have the imprint of the proton beam. When we have the converter foil and we have electron and positrons, we see a much stronger signal, which is due to electron and positrons plus all the other minor components. These are the experiments, and these were the predictions from the simulations. And this is one of those cases where, maybe the only cases I had, where the experiment provides much better results than the simulations. And we can, as I said, we can, knowing the energy deposition for each species, we can estimate the pair number on the order of 10 to the 13. So this is a very large number of pairs that we make. Right? You heard the previous talks, 10 to the 9, right? 10 to the 10. Now we can make 10 to the 13 pairs in a single shot. And the number we have is in very good agreement with the prediction from those Monte Carlo codes. We want to make sure that those are pairs, so we put them into an electron-positron spectrometer. So it's just a dipole magnet. We separate the pairs, and then we see when the magnet is powered, we see a larger signal at higher deflections, which is indication that we have deflected pairs in one direction, positrons one direction, and electrons in the other direction. And then we can compare the spectra that we measure of electron and positrons with the prediction from the Monte Carlo code. And again, in the range that we can measure, which is between 30 to 200 MeV, the agreement between the measurement and the simulations is very good. So now the final question is, how does this compare with what I said initially? So that in order to have a plasma, we need to be above this blue line. This is the density, and this is the number of pairs. These were the previous experiments, plotted in a different way. So the full color corresponds to quasi-neutrality, and the different, the empty or semi-empty means some ratio of n positrons over electrons. So in the experiment we did, we are here. So for the first time, we are in a situation where we have a plasma of electrons and positrons, where the Debye length or the skin depth in all dimensions is smaller than the size of the beam. So now we have a beam of electrons and positrons, and now the question is, can we use this beam to study plasma physics? So go back to the idea of plasma jet stability in the laboratory. And first of all, we need to create a plasma, and there are many ways to create a plasma. So we did this experiment at CERN, and those are major experiments, right? We are a very, it's university lab with limited resources, so we couldn't spend millions of dollars to do something that cost at that level. So we try to do the plasma as cheaply as possible, and we use a technique called inductively coupled plasma frequency, which is essentially the same technique that is used to make plasmas. For example, those lights are fluorescence light, which are based on radio frequency. Those ones probably not, but most of them are based on radio frequency sources. Essentially, you wrap a coil all around a glass tube, you run a radio frequency at 13.5 megahertz, and that strikes a plasma. So this is what we did. This is a meter-long plasma, and we tune the plasma density to be of the same order as the density of the pair plasma that we wanted to interact with. And so we decide to characterize this plasma using techniques that are very well known in the community, like a LAGMI probe, that are used to measure the electron densities, the electron temperature, and we all agree very well with the theory of these discharges, which is known from almost more than a century ago. So now the full experiment is this one. We have the proton beam goes into the converter target that I mentioned before. So from protons, you have electron and positrons. And we measure the property of this beam before it enters the plasma and after it exits the plasma cell. Then we characterize the entire plasma cell. The density on the plasma cell is not uniform. You have humps, right? A region of higher density surrounded by a region of lower density. So all of this has to be accounted for at some level. And then we measure the magnetic field using further rotation at the exit, almost at the exit of the plasma cell. And we also measure the spectra of the electron and positrons as they exit this plasma. So this is the full experiment. And when we do this experiment, right, the first idea is to go back to what other people have been doing in the past. And it's a group of Patrick Mugley that he did experiments at Brookhaven with 60 MeV electrons. So these are electron beams. These are quite collimated beams, so 1.5 degree divergence. And they go through the plasma. It sees here, with no plasma, when it turns on the plasma, it sees the formation of filaments. Again, this was predicted in numerical simulations. And also in our initial numerical simulations, we would predict the same thing. For a beam which is collimated, goes through a plasma, there is a residual, this is the residual proton beam, as well as the positrons, and you see formation of, in this case, a filament in the distribution at the end of the luminescence screens. So if our prediction was that in this experiment, we should see, right, at the end here, we should see a filamentary structure, some sort of filaments here, that we will measure due to the formation of these instabilities. Okay, so in order to measure the formation of an instability, we need to measure first a magnetic field. So we did this measurement using further rotation. Further rotation, essentially, you fire a laser into the plasma, and you see if the polarization of the laser is changed as it crosses the plasma. Since we knew that the fields are very small, what we did was a trick that enhances the rotation using a particular crystal. So this will be technical, but if you put a crystal inside the plasma and you fire the laser through it, this enhances the further rotation by orders of magnitude. So we can see a signal. And so the idea is, first, when there is no plasma, right? First of all, there is still a residual magnetic field due to the fact that the beam has a proton component. So there are protons on top of electrons and positrons. The proton component is not entirely zero, right? Because some of the protons still passes through. And then you can use the Biot-Savart, or you can do proper simulations with Fluka and find out that this residual field is small, in the order of 0.8 millitesla, which is within the noise of our measurement capability. Then, with the plasma, a stronger field is measured because now the instability sets in, and the instability produces a magnetic field. And we see that now magnetic field is measured, or the order, peak magnetic field, or the order of a few millitesla. So now we have a measurement of magnetic field, so now we can estimate a growth rate of an instability, which essentially means we know which was the field, the experimental field, the maximum field. We know which was the field without the plasma, so we can estimate, and we know the propagation from the start of the plasma cell to the position of the measurement. We can estimate a growth rate of the instability, which is in the order of 0.2 inverse nanoseconds. If we take the max fields, would be less than 0.5 inverse nanoseconds. So these are order of magnitude estimates of the growth rate of these instabilities. So how does this compare with what we have from the simulations? So now we try to do full-scale big simulations. So this is Pablo, who's sitting there, and Luis. They did all these simulations. So in order to do these simulations, we need to take a realistic momentum phase-space distribution of the pairs. So the pairs, as they enter the plasma, they are not just a monochromatic beam, they have the full energy distribution. You need to account for the fact that the plasma includes the protons. The background is not constant, as changing in space. You need to include that the beam has some temperature, so there is a finite divergence. And when you put all of this together, then the prediction from the simulations, which are this one at the exit of the plasma cell, agrees with what we see in the experiment, where we don't see any evidence of a filamentary structure, because that means that the instability is still at very, very early stages. And this was surprising at the beginning, because, as I mentioned before, most of the simulations that people have done, if not all, says that when you have a plasma, you have a beam, you should see kinetic instabilities to be present. And we can estimate the growth rate of our instability. Our divergence is very small, is 2%. And when the simulation is done, putting the divergence, then the growth rate, which is predicted in the simulations, right, which is one of these between these curves here, then agrees pretty well with what we see in the experimental data. So what is the bottom line here? Now this compares to the growth rate of instabilities in blazar jets. First of all, we can use quasi-linear theory. Quasi-linear theory gives us a scaling of the instability, and in this case, the faster growing instability has to be an oblique instability, because wide-band instabilities, electromagnetic instabilities will be suppressed by the finite transverse temperature. So we have a scaling for this oblique instability. This was done in the 70s by Feinberg and others. We can just rescale this quantity, because we know the density in the plasma, we know the proton density, and we know these numbers, or we can infer these numbers for the astrophysical case. So simply we can rescale the growth rate for instability based on the experimental growth rate. Then the other thing we can do, we can, from the growth rate of the instability, we can also determine which would be the saturated value of the magnetic field, and compare all of these numbers with the time scale for inverse Compton on the CMB. And when we put this on a plot, you see this is a function of the pair jet density in the blazar, which varies because it depends on which type of jets you are looking at. So the first thing that you look at are the top plot here, which tells us that the instability grows, even if in the experiment was small, it's still very fast, and this case here is still very fast, and the magnetic field becomes saturated even before inverse Compton plays a role. But the problem is that even the field grows very fast, the saturated field that we predict is much smaller than the field that you will need to explain the absence of a GeV peak in the data. So now the conclusion is that, is this responsible for, what can we say about the GeV halos in blazars? Is that it's unlikely that can be explained by beam plasma instabilities. There could be other instabilities, but all of them are slower, so they won't answer the problem. So we are left with the fact that maybe we need to consider primordial, the presence of primordial magnetic field. So I'm concluding, yeah, so there are many people involved here. So mainly was Charlie to do these experiments, and with all of us at the CERN Control Center. Thank you again for your attention.
All right, thank you very much, Gianluca. I'll come over here for the first question.
Thank you, this was great. I'm trying to refresh my memory on these blazar beams that I used to love and then forgot how much I still have them. So 2 questions, and then maybe we can talk a little bit more. So correct me if I'm wrong, you're assuming that the delta theta that you're picking, the 2%, would be the delta theta for the blazar beams. And one would expect a beam Lorentz factor of 10 to the 6 and transfer dispersion maybe of order unity. So this is actually 10 to minus 6.
No, we're not assuming that. The delta theta for the beam, so you see here. Where is it? No, the instability scales as, I'm not sure I put it here. The instability as 1 over delta theta. So the delta theta
squared.
Of the beam
okay.
Is
rescaled as well.
Is rescaled
okay,
well, yes.
Got it. Thank you. And the second question was about the saturation of the magnetic field. So you're saying this field may not be sufficient in itself, but I think the value of the saturated field also says that most of the energy is not given to the magnetic field. Yes. Or so this states that most of the energy still is in the beam. So even though the instability may grow fast, most of the energy after the instability grows is still in the beam.
Yes, that's correct. Yes.
So it may be drained by whatever other processes afterwards. So
yeah. But I mean, also the simulations, maybe Luis or Pablo can comment. Most of the energy stays in the beam, right?
Okay,
and not in the magnetic field or electric field even.
There was another question.
Hi, Gianluca. A quick question. So the geometry of the field that you're measuring, it's going around the beam, right?
Yes.
You're looking for toroidal field, but why should there be a toroidal sense of the field? Because you have both electrons and positron pairs.
Well, first of all, there is a residual proton beam, right? So there is a residual beam in that direction. And then you're going to have transverse fields due to instabilities that are still there. So the field doesn't cancel out.
Okay, but the field of the instabilities should be in both toroidal directions,
yes.
Right? So there shouldn't be an average field that you're measuring, unless you happen to hit one particular loop.
Well, in this case, you could have a large filaments, right? So it's not that you have tiny filaments and all of them cancels out. You're going to have, see, for example, even in these simulations were assumed fully collimated beam, right? The filaments that you see are still very large. So.
Sorry, the filaments you see, is what?
These are filaments, right?
I'm not sure what is shown. Can you explain what's shown?
So, well, maybe Pablo can explain better, but what you see are electrons and positrons and protons, right? And what you see is the image of the beam onto a foil as it crosses the foil, right? So this is an imprint of the beam onto a transverse foil. So what you see are electrons here and protons and positrons there.
This looks amazingly organized for a filamentation
yes.
instability.
Pablo?
Yeah.
So so I know this doesn't look like filaments, but the reason for that is you have the sea of the protons that carry a magnetic field. So what you are really amplifying is that structure. And if you look at the effect of the field spectrum, then the line spectrum, you will the proton.
Okay, but that seems a little bit of a leap of faith from there to what happens in the intergalactic space where you don't have that field, right? Okay, but one more question. Like, if there was filamentation instability and the beam of pairs should have created overdensities, right? You should have had a little overdensities of electrons and positrons. Like, you showed this Fluka simulation against the experiment where you actually measured the density of pairs, right? can you do the same thing after it passes through plasma?
Yes.
Have you done it?
Yes.
And you see just nothing?
No, we see a very homogeneous distribution again.
Okay, so nothing changed when you introduced it?
Well, something changed. The beam got larger. We have a different distribution, but there is no filaments that have been formed. So it means that the simulations, right, at least the simulations where beams were fully collimated, were not representative of that scenario. Even a very small temperature, transverse temperature, is sufficient for making that whatever electromagnetic instabilities you are considering completely dissipate and not growing fast enough.
Thanks.
Okay, I saw the one at the front first, so we'll go here.
Thank you. Just follow up your final conclusion. It's very interesting. You can put a lower limit on the ambient. This is IgM.
Yes.
Magnetic field. What's that field you inferred? Is that interesting number? I didn't.
Well, so
what is the final conclusion?
We don't put any lower limit.
Did you have a number? What is the required to get rid of the IgM magnetic field required to get? Okay.
So this is not our limit, right? This is the limit done from Fermi-Lat.
So this instability does not play any role. You need an external B field.
You need an external B field which is larger than this.
A length scale. You don't have the magnitude. So this is 10 to the minus 12?
This is around 10 to the minus 12 millitesla, right? Assuming...
this is required. You need
yes,
this thing.
We need this field.
Okay. So it's 10 to the... Is that interesting number? Is that an interesting number? I'm trying to figure... Is that interesting lower limit? I'm just trying to figure whether this is an interesting lower limit. Okay. Maybe somebody knows better.
I think there was another question. No? Any other?
At the risk of asking one of those messy astrophysical questions.
I'm not an astrophysicist, so somebody...
maybe in this discussion, why is it necessarily the primordial field that we're trying to compare against? Because I mean, all this is happening at relatively low redshift.
Yes.
So surely there's no part of the IgM that hasn't been touched by.
Well, the problem we are talking about cosmic voids here. So what produces a field in a void is much more tricky to address, right? Because there are not very efficient plasma processes in a void that can explain this level of fields. If it was just IgM, I agree with you. Yeah. It's much easier.
Well, it's just, I mean, you know, we never cease to be amazed by how much crap galaxies blow out.
Yeah.
Or they're just spewing out stuff all over the time. So and there's plenty of processes in galaxies that make magnetic fields. So especially at low redshift, I'm not. It's not my specific realm of expertise, but I'm just wondering how much it really is the primordial fields.
Yeah, you need to ask people that works in the void.
I mean, it doesn't change any of the beautiful work you've done, but yeah, it's just for the motivation.
IgM field, no limit.
I think Chris had the question.
Do you want the mic to make your good point?
My understanding is that the FR2s tend to be in group environments, and there are some giant double-lobe radio galaxies extending megaparsecs, which presumably in which the jet has pushed into a void. So I know that some of the large-scale galaxy clustering sims, which put in magnetic field and energy feedback from jets, are finding large-scale energy deposition. So I think it's a serious issue, yeah.
Yeah, I think probably we need to wait until CTA gets in operation to be able to see exactly what's around in the halo of those structures. And then people will be able to understand that.
We've got time for another question if anyone wants to ask.
Hi, Gianluca. Thanks for a very interesting talk. Possibly a naive question. This transverse temperature seems to be a very important number for you. Is it possible to control it by tuning the cascade somehow?
Yes, so we try to do that in many ways. You are somehow limited by the struggling for the particles. So we controlled in the another experiment I didn't show, we controlled it by removing the tantalum at the end. So you reduce Coulomb collisions, and that seems to increase the collimation, make it better. But again, the results is the same. You don't see, even if it's a better collimation, it's still sufficient to inhibit.
What was the difference in the point? I think 2%, did it, was it like 1%?
Something like that. I mean, do you remember, Charlie, was factor not very large. We also use a quadrupole to collimate some of the charges, but the problem is that you also diverge some others. So,
any last questions for Gianluca? If not, let's thank Gianluca again.